Modulus of rigidity. The last topic. So first of all, we did Young's modulus. Young's modulus deals with the change in length on applying force. Then we did bulk modulus. This deals with the change in volume on the application of force. This is modulus of rigidity. Modulus of rigidity deals with the change in shape. So when you apply force on a body, then its shape can change. So this modulus of rigidity is related to that change in shape. So change in shape is like say take this as a slab. This is a slab, not slab. Take a three-dimensional figure that would make it clear. Say it's a cube. Each side of the cube is L. This is the top face. So if applying a force over the cube tangentially, if I am applying a tangential over this, force over this, and assume that the base of the cube is fixed and I'm applying force on the top face, tangential force on the top face, then there is a possibility that this face gets shifted. There's a possibility that this face gets shifted. It can shift like this way. This face gets shifted. Not here. This will shift in this. So this face will get shifted. This is basically the shift in the face. This whole face gets shifted in this direction. This is the shift. I call this shift as delta L. So due to this shift, only the shape of the cube is changing. There is no change in the volume. There is no change in the length. There's only a shift in delta L. So when the shape changes, then the modulus is known as modulus of rigidity. So we write modulus of rigidity, we represent it by eta. Eta is modulus of rigidity. It's modulus of rigidity. And this modulus of rigidity is the ratio of shearing stress. Shearing stress means tangential stress and shearing strain, tangential strain. So this ratio of tangential stress and tangential strain is known as modulus of rigidity. Shearing stress we can write, we are applying a force F over this face. So shearing stress is force. Let's call this as equation number 1. We can write shearing stress as the ratio of force divided by area. That's equation number 2. F is force which is acting tangentially over the face, and A is the area of the face. A is basically the area of the face on which you are applying force. A is area of face. So that's shearing stress. Similarly, you can also calculate shearing strain. Area of face on which this tangential force acts. Tangential force acts. That's the shearing stress. And the shearing strain is the ratio of change in length divided by the original length. Delta L by L. This delta L is actually shift in the face. The length by which the face shift is delta L. That is equation number 3. So if I substitute all values here, then your eta, your modulus of rigidity is the ratio of force upon area, change in length divided by. I'm sorry, this is not change in length. This is basically the shift in phase. Length is not changing. Length is same. This is again L. It just shifts by the length. The phase gets shifted by the amount delta L. So this is modulus of rigidity. There's one more way to define this modulus of rigidity, this shearing strain, and that is, see, this side gets shifted by an angle theta. This theta is also a measure of shearing strain. You can also write that shearing strain is tan theta. And what is tan theta? In this right angle triangle, this is perpendicular upon base. So you can say that tan theta is delta L by L. This is how we calculate shearing strain. Is it clear?
Yes, sir.
Yes, sir.
So that's modulus of rigidity. This we use when there is a change in shape of the body. So we use this when there is change in shape of the body. So you have a square. It's a square slab. This is the square slab. Of side 50 centimeters. So each side of the slab is 50 centimeter. So this is square. Huh? This is square slab. Each side of the slab is 50 centimeter. This is 50 centimeter. This is 50 centimeter. Now, there is some thickness of the slab. I cannot draw three-dimensional diagram. There is some thickness of the slab, and that thickness of the slab is 10 centimeter. So you can consider this slab as a book. If I take some book, let's say this book, if I'm taking this book, and this is like the slab, and this is the thickness of the slab, which is not shown. So it's basically consider this book as your slab. This is placed in this way. I'm applying force over this narrow portion. Here, a tangential force on the narrow portion. So I'm applying a tangential force here, a force here. So the force that I'm applying is of magnitude 9 into 10 raised to the power 4 Newton. The area of this portion A is side into side, is 50 centimeter into 10 centimeter. So the area is 500 centimeters square. So that's basically 500 into 10 raised to the power minus 4 meters square. So this is force, this is area. The lower edge is riveted to the floor. That simply means this lower edge is fixed to the floor. So it cannot slide. So apply force in this way, the lower edge remains as it is. The upper edge gets shifted by some angle. So it can shift like this way. It will get shifted this way. So it gets shifted by this much amount delta L. So he's asking about delta L. How much is delta L now? So the straight formula based question, your modulus of rigidity is its force divided by area into delta L over L. You're supposed to calculate this delta L. So we can write this delta L as its force over area L by modulus of rigidity. So if I substitute all values here, your force is 9 into 10 raised power 4. The length is 50 centimeters, so that is 50 into 10 raised to the power minus 2. Divided by area, which is 500 into 10 raised to the power minus 4 into modulus of rigidity. Modulus of rigidity is this 5.6 into 10 raised to the power 9, I guess. Yes, 9. So this much meter is the displacement of the phase. Is it clear?
Yes, sir.
Yes, sir.
Okay, just note it down. That was about shear modulus. You will not get many questions of modulus of rigidity. Yes. Two strips. So that simply means you have two plates. You have connected these two plates using 4 rivets. Rivets are types of bolt. This simply means I take this book and I take some another sheet like this, and I connected them in this way, and I put 4 rivets. 4 rivets means 4 bolts. So I make one bolt here, one bolt here, one here, and one here. So I basically connected these two things with 4 rivets, 4 bolts. So these two pieces of metals are connected by 4 bolts. Now I can apply is a maximum force that I can apply here. If I exceed that maximum limit, then obviously if my force is greater than the strength of the bolt or the strength of the rivets, then these two plates will get separated. So you just have to calculate the maximum force that we can apply here. So let's say the maximum force is F max. If I'm applying a force F max here, this force is being balanced by 4 rivets. In question, it is given that each rivet carry 1/4 of the load. That means if I'm applying F max force on the plates, then force on each of the individual rivet is F max by 4. So force on each rivet is F max divided by 4. This is the force on each rivet. And if I divide this force by the area, then we will get stress. So force on, not force, stress on each rivet. Stress on each rivet is this force divided by the area of each rivet. So this is the maximum stress. So this is the maximum stress that each rivet can withstand. So is it clear up to this step, the second step?
Yes, sir, it's clear.
Okay. And that stress, the maximum value of that stress is given, which is this. The maximum value of that stress is given, which is 2.3 into 10 raised power 9 pascals. So I can say that F max divided by 4 times area is 2.3 into 10 raised to the power 9. You're supposed to calculate this F max. So you can write that this F max is 2.3 into 10 raised power 9 into 4 into area. Next, you would need the area of each rivet. Area of each rivet is this. Its diameter is 6 mm, so its radius is 3 mm. You can calculate the area. Area of each rivet is pi r square. So that's pi into r. The diameter is 6, so radius is 3 only. It's 3 into 10 raised to the power minus 3 square. So area is simply pi into 9 into 10 raised to the power minus 6. If I substitute these values here, So the maximum force that can be applied is 2.3 into 10 raised power 9 into 4 into pi into 9 into 10 raised to the power minus 6. So this maximum force comes out to be it's 36 pi into 2.3 into 10 raised to the power 3. So this is the maximum force that can be applied to the system. 36 pi into 2.3 into 10 raised to the power 3.